Throughout November, independent observers reported additional odd behaviors. In highly resolved images from multiple independent teams, narrow jets, not the broad, diffuse comae of typical cometary outflows, appeared with geometric regularity. These jets were columnated, exhibiting straight-line morphology and measurable directionality inconsistent with chaotic volatile ejection. Several jets extended in counterintuitive directions. One clearly pointed toward the sun, an anti-tail, in defiance of radiation pressure that ordinarily pushes material away. In other sequences, jets arranged themselves in repeated angular separations, suggesting mechanical patterning rather than chance. When you model 1,000 independent fragments undergoing thermal stress, the expectation is a stochastic distribution of particle velocities and directions. The data instead showed coherence. Those patterns, combined with the measured acceleration, produce a set of constraints that natural thermodynamic models struggle to satisfy simultaneously. As the scientific community sifted through models, the spectrum of plausible explanations narrowed but did not resolve. Some researchers proposed exotic natural physics, unusual electromagnetic induction as the sun's magnetic field interacted with a highly conductive body, transient phase transitions in refractory materials under intense irradiation, or even complex plasma interactions that could mimic directed thrust. Others proposed more prosaic but still remarkable possibilities. An aggregate of millions of millimeter-sized fragments with enormous collective surface area could, in principle, produce higher than expected sublimation-driven mass loss and consequently thrust without appearing as a singular bright coma. Yet the images, the compact point of light that refused to smear into a haze, consistently undermined that hypothesis. If fragmentation occurred, the fragments either acted with unnerving coordination or they concealed their individual cross-sections somehow. Against that backdrop of grappling hypotheses, the calendar approached a pivotal date, December 19th, 2025. On that day, 3I Atlas would make its closest approach to Earth, a pass at a distance that placed it squarely within range of Hubble, Webb, and virtually every major observatory on the planet. Teams from around the globe prepared simultaneous multi-wavelength campaigns, interferometric imaging, polarized light studies, high-resolution spectroscopy, radar ping attempts, and coordinated radio listening runs. The plan was simple and uncompromising. Collect as much high-fidelity data as possible during a narrow window in which the object's angular size, brightness, and geometry would offer the best chance to resolve the paradox before the visitor receded into the outer solar system and beyond our reliable observing reach. When the observation campaigns commenced, the data flowed like a tide, terabytes of frames, spectral cubes, and calibrated flux measurements. Each dataset provided constraints. Each constraint compelled model refinement. And yet, with every refinement, the object refused simple categorization. Hubble's visible light mosaics hinted at surface features that intermittently suggested reflective panels or facet-like arrangements. Webb's infrared maps captured transient hotspots that waxed and waned in cyclic sequences. Radar teams reported faint echoes that did not easily correspond to simple rough surface scattering. Radio arrays, scanning for structured transmissions, recorded faint, repeating pulses in a narrow band that correlated loosely with the 247-second periodicity some teams had earlier identified in the object's rotational signature. None of these detections were unambiguous proof of artificiality, but taken together, they formed a cumulative pattern that demanded attention. Scientists, ever the measured voices, proposed controlled experimental protocols to test hypotheses without leaping to metaphysical conclusions. Some advocated deploying high-powered radar to attempt active ranging and to measure Doppler shifts with extreme precision. Others urged exploiting the coordinated timing of the observatories to capture transient emission events across simultaneous bands to test for causality between infrared flares and radio bursts. The coordinators emphasized reproducibility. If a pattern repeats under prescribed conditions, then pattern is an observable fact, not an imagination. The ethical and practical underpinning of their approach was clear. Extreme claims require extreme evidence, yet the public dimension of the event could not be contained to conference rooms. As the images circulated, online communities and social platforms exploded with speculation. Some voices warned against alarmist interpretations, citing historical precedents where anomalies yielded mundane explanations under scrutiny. Others saw in the data a narrative of contact, an artifact of a civilization long vanished, a self-preserving probe, or even an intentionally delivered message in a guise designed to resist casual detection. The tension between scientific caution and cultural imagination created its own feedback loops as amateur observers submitted images and professional teams sifted through the noise for signals that merited attention. Amidst the clamoring interpretations, the sober reminders from senior researchers cut through. Dr. Loeb and other leading analysts repeatedly returned the conversation to the data. They urged that hypotheses be framed as testable predictions. If the object were artificial and possessed internal energy systems, then observers should see repeatable emissions, directed energy signatures, or structural regularities inconsistent with natural fragmentation. If the object were a natural but exotic phenomenon, then models should predict thermodynamic behavior that can be observed across wavelengths and replicated in analogous laboratory conditions or computer simulations. In short, the community sought an empirical adjudication. Less technical, but no less consequential, was the philosophical dimension. If 3I Atlas were merely another natural oddity, it would still expand the taxonomy of small bodies and force revisions in cometry physics. If it were artificial, the ramifications would be epochal, evidence that technological artifacts can survive interstellar transit and remain operational after eons. Proof that intelligence has taken material form in a way that endures cosmic timescales. Neither conclusion is trivial. The distinction matters for our understanding of cosmic habitability, the distribution of technological activity in the galaxy, and our assumptions about longevity, purpose, and the persistence of engineered systems. As the final weeks of intense observation approached, the collective feeling among many researchers was a mix of impatient curiosity and solemn restraint. They knew that the data set they were assembling would be the single most comprehensive record humanity could realistically obtain for a phenomenon of this kind. The object's path would take it beyond our reach within months. The window was not repeatable. The stakes were simply to gather as much empirical evidence as possible and, having done so, to let the physics speak. Whether 3I Atlas is ultimately explained as an extraordinary natural process, an as yet unmodeled physical regime, or a relic of technological origin, the episode has already influenced scientific practice. It has sharpened protocols for rapid response observation, improved cross-institutional data sharing, and underscored that even our best theories are contingent upon the data that first constrains them. In that sense, 3I Atlas is a productive discomfort. It reveals the places where certainty thins and invites inquiry where dogma once settled. For now, telescopes remain trained, instruments hum, and teams continue to scrutinize pixels and waveforms. And somewhere amid the millions of kilometers of interplanetary emptiness, the fragments travel through. The unresolved question persists. Is the stubborn, silent point of light we track the clinching enigma of an object that accelerated without a visible exhaust, that radiated unusual spectra, that followed a pathway that reads like choreography, a natural accident of physics we have not yet described? Or does it signify something that was intentionally sent, designed, and crafted? What we can say with certainty is this: the universe still surprises us. It refuses to be fully tamed by our equations or assumptions. And as 3I Atlas continues its cold, blue passage through the solar system, the record we make now will define how future generations interpret what we saw, whether a rare physical outlier or the faint, enduring echo of a mind that reached across the dark and left behind something that still, almost imperceptibly, watches back.